All right, so Chemistry B, Lesson 1.10, the ideal gas law. So far we've covered the three laws named after scientists, Boyle, Charles, and Gay-Lussac. We're going to add the ideal gas law and actually the combined gas law to your repertoire as well. But you're going to know that you've got this down when you can identify what makes a gas ideal and how to do an ideal gas law calculation. So quickly, before we get into ideal gas law, I just want to point out the combined gas law, because sometimes you might change two things, like you might change pressure and volume and you want to know what happens to the temperature, or you might change temperature and volume and you want to know what happens to the pressure. So you can actually combine Boyle, Charles, and Gay-Lussac's law together into what we call the combined gas law. All right, so if you look at this real carefully, you kind of get rid of the bottom. What you have left up top is your Boyle's law. All right, if you remove the P's, there's Charles' law. Or if you remove the V's, there's Gay-Lussac's law. All right, so you can combine all three of them together into this combined gas law. So an example of when you might use the combined gas law is you have a balloon containing 2 liters of air at STP. What will the volume of the balloon be when you double the pressure and increase the temperature to 345 Kelvin? All right, so don't let this throw you off. What is STP? All right, you have a couple different ways to remember that. STP is 1 atmosphere and 273 Kelvin, or it's 100 kPa and 273 Kelvin. I like using the 1 atmosphere one just because 1, when you throw it into an equation, doesn't usually do much, so it makes my math easier. So that means that our V1 is equal to 2 liters, our T1 is equal to 273 Kelvin, and our P1 is equal to 1 atmosphere. All right. And then what I'm going to do is I'm going to double the pressure. So P2 equals 2 atmospheres. And I'm going to increase the temperature to 345. So T2 equals 345 Kelvin. And I need to know what V2 is. All right, so I'm going to plug this into my combined gas law. I just wrote the wrong 2 there. That should be T1, sorry. And T2 is on the other side. Now let's start plugging things in. So I've got 1 times 2, 1 atmosphere times 2 liters divided by 273 is equal to 2 times my new volume over 345. All right, I'm going to cross multiply again here. So multiply these guys together. So I'm going to have 273 times 2 times V is equal to 1 times 2 times 345. So let's simplify this. So that's going to be 546 times V is equal to 1 times 2, which is 2, times 345, which is 1 times 2. Sorry, I accidentally hit the pause button there, but 1 times 2 times 345 is 690. And divide both sides by 546. All right. And I get my V is equal to 1.27 liters. All right, so these are clearly a little bit more complicated, but still, as long as you're careful about identifying your variables correctly, not too bad. All right, so this is going to be a good slide for some note-taking. So most gases that you deal with actually are not ideal gases. All right, so ideal gases are theoretical, like perfect condition sort of gases. And our equations are technically based off of that. All right, so this is a reason why when you run an actual experiment, sometimes you don't get the results you're exactly expecting, because we're assuming that our gases are going to behave like an ideal one. So the properties of an ideal gas is that gases have negligible, think about what that might mean, all right? Essentially, it means they have zero volume. They don't take up any space, which is more or less true. We're talking about really tiny molecules, but we're actually going a little step further, and we're assuming they have no volume at all, at least the actual little particles. The particles of the gas are in constant random motion, all right? Molecules are definitely always in constant motion, but sometimes they interact with each other, which makes that motion less than random. So in ideal gas, all collisions between the particles are perfectly elastic. So this means no energy is lost if they bump into each other. In reality, when gas molecules bump into each other, usually there's a bit of friction that happens, and then a little bit of their energy is lost, so they're not moving at the same speed as they were before. And the particles do not interact with each other, i.e. there's no intermolecular forces. Like there's not going to be some molecules that are polar and attract the other things. All right? So this honestly doesn't happen very often with real gases, but you do want to know what these traits are. So, which property is not attributed to an ideal gas? All right? So really, it's which of these is not something we just listed on the last slide. All right? So ideal gases, we do assume that they have negligible volume. So that is a property of an ideal gas, so that's not going to be the answer here. We also assume that they move randomly. So the collisions of the particles are inelastic, as in energy is lost to friction. That happens with real gases, not ideal ones. So that's looking very promising. The particles do not interact with each other, no intermolecular forces. Nope, that's another ideal gas attribute. So C is the right answer. All right, ideal gas law is pressure times volume equals N, which stands for moles, times R, which is this proportionality constant. It's just a number that makes the equation work. So you just got to plug it in every time you use it, times T, your temperature in kelvins. All right, so this R value, write these down. A lot of times you'll be given the value in the problem, but every once in a while the test or quiz likes to sneak one in without it in there, so I'd write these down so you have them. So here's an example of using the ideal gas law. What pressure is exerted by a 0.00306 moles of gas in a 25.9 liter container at 300 Kelvin? So just like all of our other ones, we're going to identify what we have. So we've got 0.0306 moles of gas, so that's our N. All right, liters is going to be our volume, and K stands for Kelvin, which is going to be our temperature, and here's our question, so our P equals question mark. All right, so we're going to plug this into our equation of PV equals nRT. All right, so P we don't know, volume's going to be 25.9. And that's going to be equal to 0.00306 times R. All right, since we're solving for P and we don't know what pressure we're dealing with, I can actually use either one of these. If you're given a pressure and say it's in atmospheres, then you've got to use the atmospheres version. If you're given a pressure and it's in kPa, then you got to use the kPa version. That's why there's two different options here. So I'm just going to throw the 8.31 in there. And 300 Kelvin. All right, so let's simplify the right side, get that down to one number, 0.00306 times 8.31 times 300. So that side is 7.63, and this is going to be P times 25.9. I'm going to divide both sides by 25.9. And you get P is equal to 0.29, and my units, because I used this one, is going to be kPa. All right. So you try this one on your own, see if you can get the right answer, and then start up the video and see if you got it right. All right, so it says how many moles of a gas are in a 10.0 liter container at 298 Kelvin and 203 kPa. So moles are a question mark. That's our volume. That's our temperature. And here's our pressure. All right, our pressure's in kPa, so we got to use the kPa R constant. Now let's plug this into our equation. So P is 203 times 10, and that's going to be N times 8.31 times 298. That's going to simplify to 2030. 8.31 times 298 is going to be 2,476.38 times N. I'm going to divide by this value, both sides. $2030 divided by 2476.38, and you get your N is equal to 0.82 moles.